Hello, and welcome to our project, Ultra-High Efficiency GaN-based BLDC Controllers for Advanced UAV Systems. My name is Noah, and my teammates are Justin Barker, Ted Pock, Lawrence Rowe, and Adriana Spikes. This is our presentation. For our project, we decided to cover a specific use case of gallium nitride, or GaN for short, transistors. These GaN transistors present exciting theoretical advantages compared to traditional MOSFETs. To clearly demonstrate these benefits, we targeted electronic speed controllers, or ESCs, a market area still relatively untapped by GaN technology.
So why are we using gallium nitride rather than something like silicon for our FETs? So if we look at this graph here, we can see that gallium nitride has a very high maximum switching speed, over 1 megahertz, whereas silicon is much lower, at a maximum of around 100 kilohertz. And so these faster switching speeds are also related to lower switching losses, which is going to reduce the heat output of the device, and also gallium nitride has an additional advantage of reduced conduction losses. So when the device is on, we're also losing less power due to resistance. And so due to these lower losses, that gives us two advantages: lower heat output and higher efficiency. So these are very important things to consider when we're trying to improve both the reliability and the performance of our ESC. So what is an ESC? So an ESC is an electronic speed controller, and it basically converts an input signal that's a digital signal, so basically think of it as a throttle signal, into a switched output signal that drives a motor and drives the motor phases. So these are commonly used in applications such as drones, remote control vehicles, and basically anything that has an electric motor that needs to run at a variety of different speeds is going to have something similar to this. And the performance of an ESC depends heavily on the switching efficiency of our FETs, as well as the thermal management, so how well we're keeping the temperature down, as well as the responsiveness to the input signal.
Hello, my name is Adriana Spikes, and I am the marketing and documentation team member. And for this slide, it shows what we built. And we built an ESC using GaN FETs to prove that GaN FETs have a better advantage over silicon. And we basically proved that with our results, which we'll show later down. But we basically proved that GaN FETs have improved efficiency, has higher power density, and has a better transient response, which that basically means that it operates much quicker than silicon. And we're going to show this in 4 ways during our expo. So first, we're going to show this by using these display cases here. And there's going to be a smaller display case so that you can see the ESCs up and close and personal. For the second, we're going to use this quadricopter setup right here. Then the quadricopter setup is going to be connected to the GUI. And the GUI is going to show the temperature, the voltage, the current, and the RPM of the motor. As you can see those little pros right there. And our last way we're going to demonstrate this is by using a model that we made in Blender to show off the quadricopter and the ESCs up and close. So here's our first ESC prototype. And you can see here, these are the magnetizing wires on it that we had to add to it because something was wrong with the design. Now we changed with our second prototype, which I'll show in the next slide. But you can also see the GaN FETs right here. And these are our ground plane. This is the voltage plane. And so this is our second ESC prototype schematic. And as you can see, we decreased the trace length between the first and the second one so that our GaN FET is going to be more efficient. We changed that gate drive configuration to fix the magnetizing wire situation. We corrected the gate driver schematic error, and we changed the voltage regulator for higher efficiency as well.
Hello, my name is Ted Pack, the Embedded Systems Lead, and my primary focus on this project was to build a device that can automate testing as well as data analysis. To achieve this, I built a GUI that communicates with a microcontroller. This is how we can send tests, controller ESCs, and analyze data. The microcontroller then controls the ESCs and reads relevant telemetry and sensor data. I used Python for the GUI and C++ for the control firmware. For those interested in the actual firmware code that I developed, the link is on this slide. The first tab is the Live Telemetry tab. Here, a user can control the throttle level and see all the sensor data live in an organized manner. We provide voltage, current, RPM, temperature, and an efficiency calculation. This way, one can easily see how an ESC is performing at a short glance. Next, I made a test runner tab. Here, a user can select a test type, either ramp, steady, or step. They can also select duration, as well as other parameters such as throttle levels. Finally, in the Data Visualization tab, a user can select one of the log files generated by the Test Runner tab and generate a graph that compares all 4 ESCs. Together, these features allow us to precisely test and categorize the performance of our ESCs compared to any other of the control ESCs, which we will discuss next.
To compare and characterize our GaN FET ESC versus other silicon-based designs, we purchased and characterized other commercial offerings on the market to measure the performance of our GaN ESCs. The first test that we did was measure the relative efficiency of our ESCs. What we did was measure the electrical RPM value over the instantaneous power, which is the voltage multiplied by the current. As we spun the throttle up, we found that GaN is about 61% more efficient than leading silicon ESCs at 50% throttle. We also measured the step response, which is how fast the motor and the RPM value will respond to the control input. And we found that after doing some data processing, GaN has a 47% faster step response than the next best silicon ESC. These results are very significant because it shows that the ESC that we've developed is significantly more efficient and responsive than any other of the leading ESCs in the market and in industry.